There are moments in history when a single invention changes the way humanity sees the universe. The telescope was one of those inventions. For centuries, every improvement in our ability to observe the sky has forced us to rethink our place in the cosmos. Each new generation of instruments has revealed a universe far larger, older, and more complex than anyone imagined. Today, that tradition continues with the James Webb Space Telescope. Orbiting nearly 1.5 million kilometers from Earth, Webb was designed to answer some of astronomy's oldest questions. Its enormous gold-coated mirror collects faint infrared light that has traveled across space for billions of years. Because the universe has expanded since the Big Bang, the oldest light is stretched beyond what human eyes can see. Webb was built specifically to detect those ancient signals. In a sense, every image it captures is a photograph from the distant past. Scientists expected Webb to improve existing observations with sharper images and more accurate measurements. What they did not expect was how quickly it would uncover puzzles that challenged long-held assumptions. One area attracting particular attention involves a remarkable effect predicted by Einstein's theory of general relativity. Imagine placing a heavy ball on a stretched sheet of rubber. The surface bends around the ball. Smaller objects rolling nearby naturally change direction because the sheet itself is curved. Gravity behaves in a similar way. Massive galaxy clusters bend the fabric of spacetime, causing light from galaxies hidden far behind them to curve on its journey toward Earth. This phenomenon, known as gravitational lensing, acts like a natural cosmic magnifying glass. Without it, many of the most distant galaxies would remain invisible. By combining Webb's extraordinary sensitivity with these natural lenses, astronomers can peer farther into cosmic history than ever before. The resulting images are breathtaking. Ancient galaxies appear as long glowing arcs, twisted rays, and delicate streaks of light created by gravity bending their paths across billions of light years. Yet while studying these remarkable observations, researchers noticed something intriguing. Some lensing patterns appeared slightly different from computer predictions. Not dramatically different. Not enough to overturn physics. Just different enough to encourage further investigation. Could these tiny differences simply reflect limitations in measurements? Perhaps hidden clouds of matter affected the calculations. Maybe the computer models needed refinement. Or perhaps the universe was revealing details that previous observations had never been precise enough to detect. At this stage, scientists remain cautious. Astronomy has a long history of apparent anomalies disappearing after better calibration, improved software, or additional observations. History teaches researchers not to rush toward extraordinary conclusions. Instead, every possibility must be tested. The data is checked repeatedly. Independent teams analyze the same observations. Alternative explanations are carefully examined before any bold claim is considered. That careful process is one of science's greatest strengths. Still, these subtle irregularities have inspired fascinating discussions among physicists. Some theoretical models suggest that gravity may behave in unexpected ways under certain extreme conditions. Others explore whether hidden properties of spacetime itself could leave faint signatures within gravitational lensing observations. These ideas remain speculative. There is currently no confirmed evidence that Webb has discovered extra dimensions or new laws of physics. But the telescope has provided observations precise enough to test ideas that were once confined almost entirely to mathematics. That alone marks a historic achievement. For decades, many theories describing the deepest nature of reality existed mainly on chalkboards and inside supercomputer simulations. Now, observations from Webb allow scientists to compare those ideas with real measurements from the distant universe. Whether those theories survive is another question entirely. Science welcomes failure because eliminating incorrect ideas brings researchers closer to the truth. Every observation, whether expected or surprising, adds another piece to an enormous cosmic puzzle. And as Webb continues collecting light that began its journey billions of years ago, astronomers know they are only beginning to explore what may be hidden within those ancient signals. Perhaps the greatest discoveries have not yet appeared. Perhaps the next observation will confirm existing theories. Or perhaps it will reveal another mystery no one has even imagined asking about. Whatever the answer, one thing has become clear. The farther humanity looks into the universe, the more extraordinary the universe becomes. If the first years of the James Webb Space Telescope have taught scientists anything, it is that the universe rarely behaves exactly as expected. Every observation seems to answer one question while creating three new ones. And perhaps that is the true purpose of exploration. One of the most fascinating discoveries is not a single galaxy or distant star, but the enormous framework that connects the entire universe. When we look at the night sky, galaxies appear scattered almost randomly across space. But when astronomers map the universe on its largest scales, a very different picture emerges. Galaxies gather along gigantic filaments that stretch across hundreds of millions of light years. These colossal structures connect massive galaxy clusters while surrounding enormous regions that contain very little matter at all. Together, they form what scientists call the cosmic web. This invisible framework represents one of the largest structures ever discovered. Yet there is another mystery hiding within it. The gravity produced by visible stars and galaxies is not enough to explain how these enormous structures formed or why galaxies move the way they do. Something unseen appears to provide additional gravitational influence. Astronomers call this invisible component dark matter. Despite making up a large portion of the universe's total matter, dark matter has never been observed directly. It neither shines nor reflects light, making it completely invisible to telescopes. Its existence is inferred only through its gravitational effects. James Webb cannot photograph dark matter itself. However, its incredibly detailed observations allow researchers to measure how gravity shapes galaxies, galaxy clusters, and gravitational lenses with greater precision than ever before. Each new observation helps narrow the list of possible explanations. At the same time, Webb is transforming another field of astronomy that once belonged almost entirely to science fiction: the study of exoplanets. Thousands of planets have already been discovered orbiting distant stars, but finding a planet is only the beginning. The greater challenge is learning what those worlds are actually like. Do they possess thick atmospheres? Could liquid water exist on their surfaces? What gases surround them? Using an extraordinary technique called spectroscopy, Webb can examine tiny changes in starlight as it passes through a planet's atmosphere. Every molecule leaves its own unique fingerprint. Water vapor, carbon dioxide, methane, sulfur compounds. Each chemical signature reveals another clue about the nature of worlds located hundreds or even thousands of light years away. These discoveries do not prove that life exists elsewhere. But they allow scientists to identify planets where the conditions might be suitable for life as we understand it. For the first time in human history, distant planets are becoming places that can be studied rather than simply imagined. That alone marks an extraordinary milestone. Yet perhaps Webb's greatest contribution is not any single discovery. It is the realization that our understanding of the universe remains unfinished. History shows that every time humanity builds a better telescope, reality becomes more complex. The first telescopes revealed mountains on the Moon. Later instruments uncovered countless galaxies beyond the Milky Way. Modern observatories detected black holes, neutron stars, and planets orbiting distant suns. Now James Webb is extending that journey farther than ever before. Every beam of light it collects began traveling across the universe long before our own planet existed. Those ancient photons crossed billions of light years, survived the expansion of space itself, and finally reached a telescope built by a civilization that only recently learned to leave its home world. There is something deeply inspiring about that. On one small planet orbiting an ordinary star, intelligent beings have developed the ability to study light that has been traveling since the earliest chapters of cosmic history. That achievement says as much about humanity as it does about the universe. The greatest discoveries may still lie ahead. Future observations could reveal the earliest generation of stars, improve our understanding of supermassive black holes, or refine theories describing how galaxies first assembled. Some ideas will be confirmed. Others will be replaced by better explanations. That is how science moves forward. Not by defending old ideas, but by testing them against new evidence. As James Webb continues its mission, one truth becomes impossible to ignore. The universe is not becoming smaller as we learn more. It is becoming deeper. Every answer opens another mystery. Every discovery reveals another horizon. And somewhere beyond the limits of today's observations, ancient light is still racing toward us, carrying stories that no human has ever read. Perhaps the next image Webb captures will answer one of astronomy's greatest questions. Or perhaps it will leave us with an even bigger one. Because the universe has never promised simple answers. It has only invited us to keep exploring.